Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry,
Hello everyone, and welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we are going to pop the cork on a brand new topic. I am talking, of course, about electrochemistry. Very, very interesting, very, very important stuff. After all, our entire lives basically rely on electricity at this point. It's kind of hard to imagine my life without electricity. I'm sure it's probably the same for you as well. It's how we can be together for this live stream, for instance, among many, many other things. So thank you very much for joining me. So what am I going to talk about today? Basically, we're going to talk about the relationship between electricity and chemistry, right? So without further ado, I present to you Electrochemistry Volume 1. As always, your feedback is more than welcome and highly encouraged, so please feel free to drop your thoughts in the chat or in the form of a comment if you're watching this as a video. Let me know if this is good. Let me know if it sucks. Let me know if it's helpful. Let me know if it's not helpful. Let me know what you'd like to see discussed on this channel, whether it has to do with electrochemistry or not. Whatever your thoughts are, I want to know what they are. Also, if you're interested and you're watching this live, you can call into the show using Discord. There's a link right down there in the description for you to call in if you would like to do that. I think it would be a great opportunity to talk to you voice to voice. Like I keep saying over and over again, not a lot of people take me up on that, but nevertheless, the option does exist. Another thing is that eventually, once I record 2 of these electrochemistry episodes, there's going to be a playlist called Electrochemistry live streams. As of this moment right now, it does not exist because I'm doing my first one. So once I do 2 or more, I will compile them into a playlist called Electrochemistry live stream. So if you're watching this in the form of a video later, it probably exists, but at this point in time, it doesn't. So, all right. So like I said before, we're basically looking at the relationship between chemistry and electricity, right? And so the main idea with electrochemistry is that there's a certain type of chemical reaction that is used to generate electricity. And those types of chemical reactions that are used to generate electricity are called oxidation-reduction reactions. So I think at this point in your chemistry education, if you're at your electrochemistry chapter, you should have at least somewhat of an understanding of oxidation-reduction reactions. But in case you don't, I actually do have some content related to oxidation-reduction reactions, also called redox reactions. I'll be calling them redox reactions throughout the entirety of the live stream going forward. Just easier to say than oxidation reduction. So if you feel a little rusty, see what I did there? Rusty, oxidation. If you feel a little rusty in your understanding of redox, I do have like a 2-part video series, Redox Part 1, Redox Part 2. Those links, of course, are down there in the description. So we are going to review what redox is, what oxidation is, what reduction is, what oxidation states are, and how to assign oxidation states to atoms within chemical formulas and chemical equations and this and that. But we're going to do that review somewhat quickly. And if you're not satisfied with your understanding of redox at the end of this presentation, then I would encourage you to refer to those links, refer to those videos that I've provided, and that will that's going to be a more thorough explanation. We're going to go through things pretty quickly, and then we're going to end things in the stream by learning how to balance the equations that are associated with the redox reactions occurring in acidic solution and in basic solution. So that's going to be the rest of the stream going forward. It might seem a little dry, it might seem a little boring, and for that, I want to apologize, but nonetheless, it is very, very important that we have a rock-solid understanding of redox reactions so that we can better understand how redox reactions are used to generate electricity. Got a message in the chat from Rizhab Sharma. It says, hello. Hello to you. I apologize for butchering your name, but Thank you for joining us. All right, so that's redox reactions. So basically, we're going to, like I said, we're going to kind of bring ourselves up to speed on redox because perhaps it's been a while since you've studied this. Perhaps you're a little rusty on it. So let's talk about it. So basically, what is oxidation? What is reduction? Well, oxidation, simply put, is the loss of electrons. So if something loses electrons, then it's being oxidized. It's undergoing oxidation, right? And conversely, reduction is the gain of electrons. If something is gaining electrons, it is being reduced. It is undergoing reduction. And there's a cute little mnemonic called oil rig that can help you understand which is which one is losing, which one is gaining. So oil stands for oxidation is losing, and then rig stands for reduction is gaining. So there's like a quick, nifty little way to remember which one. Oxidation is the loss of electrons, and reduction, of course, that's the gain of electrons. And so let's look at an example of a simple oxidation reduction redox reaction. So this equation right here, it describes the formation of hydrogen chloride from elemental hydrogen and chlorine, right? We have H2 plus Cl2 yields 2 HCl, right? This is an example of a redox reaction. Now, it may not be immediately apparent that this is a redox reaction because it doesn't really look like anything has lost or gained electrons, right? It doesn't look like anything has lost an electron to form a cation. It doesn't look like anything has gained an electron to form an anion, but this is indeed a redox reaction, and I'll explain why. So if you take a look at elemental hydrogen, H2, elemental chlorine, Cl2, right? What do these molecules have in common? Well, what they have in common is that they are connected by a nonpolar covalent bond. And what that means is that the electrons are being shared equally among the two bonded atoms in the case of both H2 and Cl2, right? So these atoms are essentially electrically neutral, right? They don't have any full or partial charge, right? But when they become HCl, what happens is when the hydrogen forms a bond with the chlorine, that bond, those two electrons that compose that single covalent bond between the hydrogen atom and the chlorine atom, are shared unequally between the two atoms. And this unequal sharing is caused by differences in electronegativity. Chlorine is more electronegative than hydrogen, which means it has a greater tendency to pull electrons toward itself in a chemical bond, right? And so as a result, chlorine acquires a partial negative charge. That's what this Greek lowercase delta means, partial negative charge. And hydrogen, having lost a little bit of electron density from the chlorine just hogging up those electrons in that bond, acquires a partial positive charge, right? And so what's happening here, right? Hydrogen goes from a state in which it's sharing electrons equally and it's completely electrically neutral to a state in which it has lost a little bit of electron density and has acquired a partial positive charge, right? Chlorine, on the other hand, has gone from a state in which it's electrically neutral to a state in which it has gained some electron density and it has acquired a partial negative charge, right? And so hydrogen has lost a little bit of electron density, and so hydrogen has undergone oxidation. Hydrogen has been oxidized, right? Chlorine has gained a little bit of electron density, and so chlorine has been reduced. Chlorine has undergone reduction, right? So we can see here that you don't have to necessarily gain an entire electron to undergo reduction. You don't necessarily have to lose an entire electron to undergo oxidation. You can lose like partial electron density to undergo oxidation. You can gain partial electron density to undergo reduction. And so how do we keep track of all this? How do we keep track of what's undergoing oxidation and what's undergoing reduction in a very simple and straightforward way? And the answer is that we use something called oxidation states. right? And again, all of this should be familiar to you. Hopefully some of this stuff is kind of ringing a bell with you. I really, really hope it is. But in case it isn't, we are, like I said, we are going to review these things briefly, but we're not going to do it in a very thorough way. And if you want a more thorough explanation of oxidation states, again, I highly recommend that you check out my Redox videos. The links are in the description. So what is an oxidation state? Well, an oxidation state is basically like the charge that an atom would have if all of the electrons that are shared between atoms were assigned to the atom that attracts the electrons most strongly. So let me repeat that real quick because I know that was probably a little bit confusing. So an oxidation state is basically the charge that an atom would have if all of the electrons that were shared between atoms were assigned to the atom that attracts the electrons the most strongly. So I'm going to take you guys to the whiteboard real quick just to make sure that we kind of understand this, right? So in the case of that hydrogen chloride molecule, that HCl, right? So I'm just going to draw like a little structure for HCl, right? So we know that the bond between the hydrogen and the chlorine is composed of 2 electrons, right? And so in the context of oxidation states, basically we are treating the chlorine like both of the electrons that are in that single covalent bond belong to the chlorine. And so therefore we would give that a -1 oxidation state. We kind of treat it like it's gained an entire electron, even though technically it hasn't. It's just gained a little bit of electron density, right? And likewise, we would treat the hydrogen as if none of these electrons in this bond belong to it. And so we would give it a +1 oxidation state, right? And so I'm going to take you guys back to the PowerPoint real quick, and we're going to discuss the 5 rules for how to assign oxidation states to atoms. And then once we understand those rules, then we'll go through the balancing of redox equations, both in acidic solution and in basic solution. So the first rule when assigning oxidation states is that the oxidation state of a free element is always 0, right? So if you have like elemental hydrogen, elemental chlorine, elemental bromine, elemental fluorine, elemental aluminum, any element by itself, right, with no charge, always has an oxidation state of 0. So rule number 1, pretty straightforward, pretty easy to understand. Rule number 2, also pretty straightforward. Rule number 2 is that the oxidation state of a monoatomic ion, so that means a single atom that has a charge, right? So like sodium ion, Na+, oxide ion, O2-, things like that. Any monoatomic ion, the oxidation state of that monoatomic ion is going to be equal to its charge, right? So Na+, the sodium ion, that sodium atom is going to have an oxidation state of +1. Oxide, O2-, it's going to be equal to the charge, right? The oxygen and the oxide ion would have an oxidation state of -2, right? So rules number 1 and 2, pretty straightforward. Moving right along to rule number 3, I'm going to move myself a little bit here. So let me see. I got to grab my... Okay, here we go. Just had to move myself out of the way there. So rule number 3 is that the sum of the oxidation states of the atoms in a molecule or polyatomic ion is equal to the charge of that molecule or polyatomic ion. Obviously, if it's a molecule or like an ionic formula unit that's electrically neutral, the sum of those oxidation states is going to be equal to 0. And if it's a polyatomic ion, right, a group of atoms that has an overall charge, the sum of the oxidation states of that polyatomic ion is going to be equal to the charge of that polyatomic ion. So Rizba says, so that means H2 has no oxidation state. No, H2 has an oxidation state of 0. We wouldn't say that it doesn't have an oxidation state. It does have an oxidation state, but it would be 0. Thank you for your comment. Chances are, if you have a question like that, other people have a question like that too. So thank you very much. So let's move right along to rules number 4 and 5, starting with rule number 4. So rule number 4 tells us that metals in compounds always have positive oxidation states. And if it's a group 1A metal, alkali metal like sodium or lithium or potassium or rubidium or cesium, all of those are going to have oxidation states of +1. And if it's a group 2A metal, like magnesium or calcium or barium or something like that, all those group 2A metals, those alkaline earth metals as they're called, are going to have oxidation states of +2, right? And finally, we're going to move on to the fifth rule about oxidation states, which is that, as I need to move myself over once again. All right. So rule number 5 is that in compounds, nonmetals are assigned oxidation states according to this table down here. So basically, the way this works is that if you have these elements in your formula, you're going to assign oxidation states to them in the following order. You're going to start with fluorine, if there's fluorine in it, then hydrogen, then oxygen, then halogens, group 7A, then group 6A nonmetals, and then group 5A nonmetals like nitrogen and such, boron and stuff like that. So basically, for fluorine, it's -1, hydrogen, it's +1, oxygen, -2, group 7A elements, -1, group 6A elements, -2, group 5A elements, -3, and this arrow down here sort of points downward in terms of decreasing precedence. So for instance, if it has fluorine and hydrogen in it, you would start by assigning oxidation to the fluorine atom first, and then you would save the hydrogen atom for later, and so on and so forth. That's the correct way to interpret this table when you're assigning oxidation states to nonmetals, and it's sort of ambiguous. All right, guys, so now that we are sort of back up to speed when it comes to oxidation states, what oxidation is, what reduction is, how to assign oxidation states to atoms. And again, like I said, if this is not a thorough enough explanation for you, then I do have those videos. The links are in the description. I highly recommend you watch those if you're still feeling confused about how to assign oxidation states. So with that in mind, we are going to move on and we are going to learn how to balance redox reactions. We're going to balance the chemical equations associated with redox reactions occurring in acidic solution and in basic solution. So the technique that we're going to use is called the half reaction method of balancing. And so you basically, what you do is you take the chemical equation and you split it up into half reactions, one for oxidation, one for reduction. You balance each half reaction, and then when you're done balancing the half reactions, then you add them together to get your overall balanced chemical equation for your redox reaction. So it is a 7-step process. If you follow the steps in order and you follow them correctly, then that will lead you to the correct balanced chemical equation for your redox reaction every single time. And the steps differ slightly depending on whether the reaction is taking place in acidic solution versus basic solution. And we are going to elaborate on that as we go forward throughout the presentation. So let's go to the whiteboard and we're going to bang out a couple of problems. We're going to do one problem for a redox reaction in acidic solution and one problem for a redox reaction occurring in basic solution. So, okay, we are at the whiteboard. I've got a couple of equations written down, so allow me to sort of write them out and we will start solving the problems. So the first equation that we're going to look at, and we're going to assume that this equation, this reaction, is occurring in acidic solution, right? So we're balancing the following redox reaction occurring in acidic solution. So here's the reaction. So we're going to have NO3 minus, that's the nitrate ion, plus SN2 plus, that's the tin 2 ion, SN2 plus, yields SN4 plus, the tin 4 ion. Hey, I just got a new subscriber. Thank you, whoever that was. And we're also going to have nitric oxide, NO, right? So this is our chemical equation right here. And we are going to balance it taking place in acidic solution. So the first step, right? The first step in solving a problem like this, I actually have all the steps sort of written down in my PowerPoint. I just got to sort of copy and paste them into the whiteboard. That's the technique that I'm sort of using. I've never done it in this way before, but hopefully it works. So the first step, and I'll just stick it down here on the bottom right, is to assign oxidation states to all of the atoms in this chemical equation, and we're going to identify what is being oxidized and what is being reduced, right? So we're assigning oxidation states to everything in this entire chemical equation. Rizhab says, I think P block can have many oxidation states and group 1 can only have one. Yes, in general, that is correct. That is a very good observation. Thank you for making it. All right, so we're going to assign oxidation states to everything in this equation, right? So let's start with the atoms in this nitrate ion, NO3 minus, right? So if I pulled up that table of nonmetals earlier, right? We have two nonmetals, nitrogen and oxygen. We would see that oxygen takes precedence over nitrogen, and we would give it an oxidation state of -2, right? Oxygen has an oxidation state of -2, according to that table of nonmetals that we looked at a moment ago. And nitrogen, what is the oxidation state of nitrogen going to be? Well, we know that the sum of all of the oxidation states for all of the atoms is going to be equal to the charge of the polyatomic ion. In this case, the charge is -1, right? So that's rule number 3. The sum of the oxidation states is equal to the charge of the polyatomic ion, right? And so we have 3 oxygen atoms at -2 apiece. So I'm going to set this up like an algebraic equation, right? I'm going to let X represent the oxidation state of nitrogen, right? And so X plus the oxidation states of all those oxygen atoms, right? X plus, we can say 3 times -2, right? Because 3 oxygen atoms -2 oxidation state for each one of them is equal to the charge, which is -1, right? X plus, I don't know why I said 3x, what I meant was 3. Oh, wait. Yeah, I just got confused. I got confused between the variable x and the multiplication symbol, so 3 times -2. So basically what this means is we have x minus 6 is equal to -1, and algebraically, if we just add 6 to both sides of this, we get x is equal to plus 5, right? So basically, what did we do? We know that the oxidation state of oxygen is -2, and then we use that rule number 3, where the sum of all the oxidation states has to be equal to the charge of the polyatomic ion to algebraically solve for the oxidation state of nitrogen, which we now know is plus 5, right? So that's basically how to do that, right? Now for this tin, right, we know that the oxidation state of a monoatomic ion is equal to its charge. So the oxidation state of this tin is +2. And if we follow that same logic, we know that this tin ion over here, that's going to be +4, right, because that's a monoatomic ion. And then if we apply the same rules that we used for this NO3 minus over here, we get an oxidation state for the oxygen of -2. And since the sum of the oxidation states of everything must be equal to the charge of this molecule, since it's just a plain old neutral molecule, the sum of these is going to be 0. And so that means that the oxidation state of nitrogen in nitric oxide must be +2, right? So now that we know what all of the oxidation states are, we can easily see what's being oxidized and what's being reduced, right? If something's being oxidized, that means that its oxidation state is going up. If something is being reduced, that means that its oxidation state is going down, right? And so what is being oxidized? What is being reduced? Well, it looks like the nitrogen is going from a +5 oxidation state to a +2 oxidation state. So it's decreasing, which means that the nitrogen is being reduced, right? And we also know that the tin, its oxidation state is going up, going from +2 to +4. So the tin is being oxidized. So the tin is being oxidized and the nitrogen is being reduced, and the oxygen isn't being oxidized or reduced, okay? So step 1 is complete. We assigned oxidation states to everything. We know that the tin is being oxidized and the nitrogen is being reduced. And so now we can delete that and we can move on to the second step, right? The second step of this process here. So let me grab the directions for step 2 and paste it back into the whiteboard here. So let me enlarge this. By the way, if you find this stream valuable, I would highly appreciate your support in the form of leaving a thumbs up on the video, not just for my own ego, but because liking is sharing. When you like a video, it actually promotes it just a teeny tiny bit in the algorithm, and I, of course, need all the help I can get in terms of discovery and exposure and stuff like that. And if you would like to support this stream monetarily, that would be more than welcome as well. There's a couple ways to do that. You can send a super chat, pretty easy to do, or you can donate via Streamlabs. There's a link down in the description. It says support the stream. If you follow that link, you can donate through PayPal. You can do text-to-speech donations and fun stuff like that. It's a little bit more difficult than sending a super chat, but Streamlabs takes much less of a cut than YouTube does with their super chats, so more of your donation goes to support the stream if you choose to do that. All right, so with that out of the way, let's move on to step 2. So step 2 tells us to separate the reaction into 2 half reactions, one for oxidation and one for reduction, right? So I'll just go ahead and label my reactions. I'll put OX for ox, and I'll put RED for reduction, right? And so we know what's being oxidized, we know what's being reduced, right? The tin is being oxidized, so I'll go ahead and write the tin half reaction right here, where we have SN2 plus yields SN4 plus. That's my oxidation half reaction. And then for my reduction half reaction, that's going to be the one where you have nitrate and then nitric oxide. So we're going to have NO3 minus yields NO2. So step 2 is now complete. We have separated our reaction into 2 half reactions. So let's move on. We're going to go ahead and delete that. We're going to move right along to step 3. So bear with me while I sort of copy and paste it into my software here. Okay. So step 3, I've sort of highlighted this one because step 3 is where the procedure starts to differ depending on whether your reaction is taking place in acidic solution versus basic solution, right? So this step 3 applies to acidic solution, and in the next problem we'll do it in basic solution. We'll see how it differs between acidic and basic solution. So step 3, it says to balance each half reaction with respect to mass, and you carry out these bullet points in order from top to bottom. So the first thing to do is to balance all elements other than hydrogen and oxygen. Then you balance oxygen by adding water, and then you balance hydrogen by adding H+. Okay, so if we look at our oxidation half reaction, where we have SN2 plus becoming SN4 plus, balance all elements other than hydrogen and oxygen. Well, that's already done, right? We have one tin atom over here. We have one tin atom over here, so that's good. It says balance oxygen by adding H2O. That really doesn't apply to our oxidation half reaction, so we can skip that. And it says balance hydrogen by adding H+. Again, there's no hydrogen in this oxidation half reaction, so step 3 pretty much doesn't apply to our oxidation half reaction. Now, if we look at our reduction half reaction, we have nitrate ion becoming NO. Wait, I don't know why I put NO2 here. Excuse me. That should just be NO. My apologies. NO3 minus becomes NO. So if we look at our reduction half reaction, we are actually going to have to do step 3 for this, right? So it says balance all elements other than hydrogen and oxygen. Well, that's done, right? Because we have one nitrogen on both sides of this reduction half reaction, right? And then it says balance oxygen by adding water, right? So notice that we have different numbers of oxygens on both sides of this equation. We have 3 oxygens on the left, we have 1 oxygen on the right. So the question then becomes, how many water molecules do we need to add to the right-hand side of the equation to get 3 oxygens? Well, that would be 2. We need to add 2 waters, right? That'll give us 3 oxygens on both sides. And then we need to balance hydrogen by adding H pluses. So then we need to add some H pluses to the left-hand side of this reduction half reaction to get how many hydrogens? Well, it looks like we have 2 water molecules, each with 2 hydrogens apiece. So that looks like a total of 4 hydrogen atoms on the right-hand side of this. And so I need to add 4 H pluses, right? So again, what did we do? We balanced all elements other than hydrogen and oxygen. That was already done for us, right? Then we balanced oxygen by adding water. Then we balanced hydrogen by adding H plus. That's step 3 for reactions taking place in acidic solution. So now we are ready to move on to step 4. So bear with me while I paste step 4 into this. So there's a couple of messages in the chat. Somebody says, you single-handedly got me an A+ in Gen Chem 1. Oh man, I can't take full credit for that. That was all you, brother. But I'm glad I could help. Thank you for sharing that. I love your kind words. Yuri V says, you are amazing. Right back at you, sir. Thank you very much. Bloodsport says, hey, Ben, doing great. Thanks, brother. Appreciate it. Thomas Shelby says, hello, Ben. I prefer your videos over school lectures, but unfortunately it's time for school in India. See you later. All right, man. Hope you have a great school day. Wow, I really, really appreciate all the kind words today. But I don't want to lose focus, so let's get back into the problem. We're on step 4. Thank you guys very much. You guys are awesome. You know, I gotta be honest. I was not expecting to get this level of engagement and support on Super Bowl Sunday. I guess you guys are just like me. You don't really give a shit about the Super Bowl, which is good. All right. So step 4 says to balance each half reaction with respect to charge by adding electrons. Balance each half reaction with respect to charge by adding electrons, right? So we need to add electrons. Of course, electrons are negatively charged, right? So obviously, if we look at our oxidation half reaction, the charges are not the same. We have a charge of +2 on the left and +4 on the right. So it looks like we need to add 2 electrons, right? Because if we have 4+ charge coming from the tin ion, and then we have 2 electrons, that'll reduce the charge by 2, giving us 2+ charge on the right-hand side of our oxidation half reaction. And so that takes care of the oxidation half reaction. And then if we look at our reduction half reaction, looks like I'm going to have to give myself a little bit more room. Let me sort of drag this equation over here, a little bit over here, just so I can give myself some more room, right? So we're going to have to add some electrons to the reactant side, the left-hand side of our reduction half reaction. How many electrons do you think we need to add here? Well, we have 4 H pluses. We have 1 NO3 minus, right? So we have 4+ over here, 1 minus over here. So it looks like before we add any electrons, we have a charge of 3+ or +3. We have a neutral or 0 charge over here on the right. And so it looks to me like we need to add 3 electrons to give us an overall 0 charge over here on the left side to match the 0 charge that's over here on the right side. Okay, so that's step 4. There's only a couple more steps. It's a 7-step process, so we've already gone more than halfway there, so to speak. So let's move on to step 5. And again, I apologize if this is a little dry and boring. We are going to get into the more interesting stuff to learn exactly how redox reactions are used to generate electric current in the next stream. But for now, we just have to make sure we have this solid understanding of redox reactions. It is absolutely necessary that we understand this stuff. Okay, so step 5 says to make the number of electrons in both half reactions equal by multiplying one or both half reactions by a factor, right? So clearly, the number of electrons in our half reactions are not equal. One of our half reactions has 2 electrons, the other has 3 electrons, so we need to make those equal somehow. So basically what we're trying to do is we're trying to find like the least common multiple of our numbers of electrons, right? So what's the least common multiple of 2 and 3? Well, that would be 6, right? So we need to make the number of electrons in both half reactions equal to 6, and that means that we're going to multiply our oxidation half reaction by 3, and we're going to multiply our reduction half reaction by 2, right? So when we multiply an equation by a factor, what we're doing is we're multiplying every single coefficient in the equation by that factor, right? So if we're multiplying our oxidation half reaction by 3, we're going to multiply every coefficient over here by 3. So that's going to give us 3 of these tin 2+ ions. Let me move this over here so I can sort of fit the coefficient in. Didn't mean to do that. I'm going to move this over here just a little bit so I can snug that 3 in right there. So we're going to put a 3 in front of that also. And then the number of electrons is going to be 3 multiplied by 2, which is going to be equal to 6 electrons, right? So we just multiplied our oxidation half reaction by 3. Got a couple more messages in the chat. It says best channel. It says Thomas Shelby. Yeah, right now I'm ready to go to school. Cannot be able to take out the time. Yeah, I don't know. I kind of have the same opinion about academia as you guys do, but it does get better, I promise. Just power through it. And you came to the right channel. What can I say? All right. So for reduction, we're going to multiply everything in this reduction half reaction by 2. Of course, when we multiply the 3 electrons by 2, that's going to become 6 electrons. The 4 H pluses, when we multiply that by 2, that's going to become 8 H pluses. The nitrate ions, the NO3s, that's going to become 2 NO3s. So I'll just get that in there. 2 NO3 minuses. The nitric oxide, I'm going to move this arrow just a little bit to the left. Nitric oxide, that's going to be 2 when we multiply it by 2. And then our 2 water molecules, when we multiply that by 2, it's going to become 4 water molecules. Okay, so now we have our half reactions basically manipulated so that the number of electrons in both half reactions is the same, which happens to be 6 electrons for this particular problem. So step 5 is done. We are all but done. We are going to move on to step 6. Here we go. Let me just copy and paste it in here for you real quick. So, okay. So number 6, it says, to add the 2 half reactions together, canceling electrons and other species as necessary. Okay, so we're going to add these 2 half reactions together. We're going to see what we can cancel out. Obviously, the electrons are going to cancel out. 6 electrons on the right-hand side of our oxidation half reaction is going to cancel out with the 6 electrons on the left-hand side of our reduction half reaction. And it doesn't look like anything else cancels here, so I'm just going to write the equation in blue. And I'm going to actually, what I'm going to do is I'm just going to erase this stuff up here because we don't really need it anymore. And I'm going to use this valuable space to write the equation for the combined redox reaction. So our final balanced redox equation, it's going to look like this, where we have 3 SN2+ ions plus 8 H pluses plus 2 NO3 minuses, and that's going to yield 3 SN4 pluses plus 2 nitric oxide molecules plus 4 water molecules. So that is our combined balanced redox reaction. And then now that we've done that, I'm just going to double check, make sure this is correct. 3 tin, 8 H plus, 2 nitrates, 3 of those, 2 of those, 4 of those. Okay, so I'm going to erase all this stuff because I'm going to use this space in just a moment. So that's step 6. We have one more step to go, and this problem will be done. We're going to do one more, and then we're going to be finished for the night. You guys can go back to watching the Super Bowl if that's your thing. All right, so here we go. So step 7. Step 7 is pretty straightforward. If I can just copy and paste the darn thing. Let's see. Excuse me. Step 7 is simply to verify that the reaction is balanced. So to verify that this reaction is balanced, basically what I'm going to do is I'm just going to make a little table with an R and a P column. R stands for reactants, and then P stands for products. And we're going to make rows for every single element, right? So what are the elements that we have? We have tin, we have hydrogen, we have nitrogen, and we have oxygen, right? Those are the 4 elements that we have. So let's make sure that we have the same number. Oh, and last but not least, we also have charge. We can't forget the charge, right? This thing has to be balanced both atomically and electrically. Absolutely important that we remember that. So if we look at tin, we have 3 tin over here, 3 tin, so we have 3 on both sides. Hydrogen on the left-hand side, we have 8 hydrogen atoms. We have 4 times 2, which is 8 hydrogen atoms over on the right-hand side. So far, so good. For nitrogen, we have 2 nitrogens over here in those 2 nitrate ions. We have 2 nitrogen over here in our 2 nitric oxide molecules over on the product. So that's good. Nitrogen checks out. Oxygen, what do we have? We have 2 times 3, which is 6 oxygen atoms on the left-hand side. How many oxygen atoms do we have on the right? Well, we have 2 oxygens in our 2 nitric oxide molecules, plus another 4 oxygens from our 4 water molecules. So we have 6 oxygens over on the right-hand side. And then finally, let's look at the charge, right? So the charge, we have 6 plus or plus 6 from this, because we have 3 of these ions with 2 plus apiece. So that's 6 plus, or I'll just say plus 6. We have 8 plus over here, so we have plus 8 over there. And then over here we have minus 2 from those 2 nitrates, right? So we have 6 plus 8, that's 14, minus 2, so that's plus 12 on the left-hand side. And on the right-hand side, do we also have plus 12? Looks like we do, because we have 3 of these tin ions with a charge of plus 4 apiece. So everything checks out, right? This thing is completely balanced, and that is how you solve or balance a redox equation for a reaction taking place in aqueous acidic solution. All right, folks, so that was it for the acidic solution. So like I said, we're just going to do one more problem. We're going to do one for basic solution, and then we're going to call it a night. And next week, we'll get into the interesting stuff where we talk about voltaic or galvanic cells, talking about standard electrode potentials and things like that. It's going to be really, really cool, really interesting. And I hope you join me next week. I really, really do. I really, really have enjoyed the engagement that I've gotten in this stream. You guys, you're the real MVPs. Let me tell you that. Okay, so this equation, again, we are going to assume that the reaction is taking place in basic solution. And what does the equation look like? The equation looks like this. So we have SO3 2 minus plus MnO4 minus, that's the permanganate ion, and that's going to yield SO4 2 minus, the sulfate ion, plus Mn2 plus. Got ahead of myself a little bit there. All right, so this is our chemical equation occurring in basic solution. So we need to balance it, right? So again, I'm just going to take my time here. I'm going to paste each step in here, and we're going to take care of this problem, solving this problem with the 7-step process that we used in the last problem. But again, the steps are going to be a little bit different since we're in basic solution rather than acidic solution. So the first step is to, again, assign oxidation states to all of the atoms, identify what's being oxidized and what's being reduced, right? Pretty straightforward. So let's start with the atoms that are in this sulfite ion over here, SO3 2 minus. Well, oxygen, that's going to carry an oxidation state of -2, right? Because of that table of nonmetals, right, where you have decreasing precedence. Oxygen lies higher on that table than sulfur does, so we're going to give it an oxidation state of -2. We also know that the sum of these oxidation states is going to be equal to the charge of the polyatomic ion. In this case, the charge is -2. And so we can solve this algebraically. If we let X represent the oxidation state of sulfur, we know that X minus 6 is going to be equal to -2. Why is it X minus 6? Well, because we have 3 oxygen atoms, each with an oxidation state of -2. So the sum of this represents the sum of the oxidation states, and this right-hand side of the equation represents the charge of the polyatomic ion, right? And so if we solve this equation, we get X is equal to +4, right? We just added 6 to both sides of this equation. So we know that the sulfur has an oxidation state of +4 in this sulfite ion, this SO3 2-. So let's take the same approach with the permanganate ion, the MnO4-. We know that oxygen, for reasons that we discussed a moment ago, it's going to carry an oxidation state of -2. So we can set this up like an algebraic equation, just like we did before, where if we let X represent the oxidation state of the manganese, it's going to be X minus 8 is equal to -1. And again, it's X minus 8 because 4 oxygen atoms, each with an oxidation state of -2, it's going to represent -8, right? So X minus 8 is equal to -1, the charge of this ion, and so X is going to be equal to +7, right? So this is +7 oxidation state for that manganese right there. Let's do the same thing for our sulfite ion, or our sulfate ion. I'm mixing these up, I apologize. SO4 2-, sulfate ion, right? So we know that oxygen is going to be -2, and if we let X represent the oxidation state of sulfur, it's going to be X minus 8 is equal to -2, because we have 4 oxygen atoms, each with an oxidation state of -2 is going to equal the total charge, which is -2 of this ion. So we get X is equal to +6. So sulfur is going to be +6 in this case, and we're going to erase all of that. And then we're going to save the easiest one for last, right? The charge of any monoatomic ion, or the oxidation state rather, of any monoatomic ion is going to be equal to its charge. So in this case, it is +2, right? So now that we have assigned oxidation states to every atom in this equation, we can identify what's being oxidized, what's being reduced. Looks to me like the sulfur is being oxidized because its oxidation state is going up. It's going from +4 to +6. Looks like the manganese is being reduced because its oxidation state is going down. It's going from +7 to +2. So sulfur is being oxidized, manganese is being reduced. So that takes care of step 1. Step 2, anybody in the chat remember what step 2 is while I fetch it from the PowerPoint and paste it in here? Just want to make sure people are listening. Although maybe you are listening, maybe you just haven't been watching for the entirety of the stream. I don't know exactly who's been watching and for how long. But step 2, looks like I already have it pasted in here, is to separate the reaction into 2 half reactions, one for oxidation, one for reduction, right? So I'll label my oxidation half reaction with OX. I'll label my reduction half reaction with RED. So the oxidation half reaction, that's going to be the one where sulfite becomes sulfate, right? SO3 minus becomes, whoops, shouldn't have been a plus sign, it should be an arrow. SO3 minus becomes SO4, should be SO3 2-, excuse me. SO3 2- becomes SO4 2-, right? Because the sulfur is being oxidized, right? And then our reduction half reaction is going to be MnO4- yields Mn2+, right? So step 2 is complete. We have separated our reaction into 2 half reactions. We identify what our oxidation and our reduction half reactions are. So moving on to step 3. So step 3, this is very, very important because step 3 for reactions in basic solution is different from step 3 for reactions in acidic solution. And I've highlighted the part that is different, the part that applies to basic solutions, but not acidic solutions. So I'm going to try to enlarge this without, how do I do this? Well, you know what? I think I think since I got my half reactions, I no longer need this equation up here. So I'm just going to delete all that stuff. And then what I'm going to do is I'm going to move my half reactions up just a little bit so that I can give myself some room to, if I can get the darn thing to work, so that I can give myself some room to sort of enlarge my step 3 here, because I really want to make sure that we can all see that pretty well. So I'm just running out of room, guys. All right, I think this is probably the best I can do here, and I'll go ahead and make myself a little bit smaller so that I can get these half reactions in there. All right, so step 3, right, is to balance each half reaction with respect to mass, right? So the first step is to balance all elements other than hydrogen and oxygen. Notice that in both our oxidation and our reduction half reaction, that step is done, because in our oxidation half reaction, we have 1 sulfur on both sides. Reduction half reaction, we have 1 manganese atom on both sides, so that's done. We can skip that. The second step is to balance oxygen by adding water, right? Balance oxygen by adding water. So we're going to start with our oxidation half reaction. Notice that we have 1 more oxygen on the right-hand side than we do on the left-hand side. So I'm going to add 1 water molecule to the right-hand side. Then we're going to balance hydrogen by adding H pluses, right? So we have 2 hydrogens over here on the left now. So I need to add 2 hydrogens, or 2 H pluses rather, over here on the right. Now this highlighted part, this is the important part for basic solution that does not apply to acidic solution. So what we're going to do is we're going to neutralize H plus by adding 1 OH minus, 1 hydroxide ion for every H plus in the equation. And we're going to add the same number of OH minuses on both sides of the equation, right? So since we added 2 H pluses over here on the right, I'm going to add 2 OH minuses, and I'm going to add that same number of OH minuses to the left-hand side of this equation as well, 2 OH minuses, right? Let's see if I can move these a little bit. You know, these equations, they really do tend to get long-winded. It's been a challenge trying to fit everything that I need to fit into this whiteboard here, because they get very, very long. Okay, well, I think we can all see that it's 2 hydroxides on the left and 2 hydroxides on the right. Now, one thing that's important to understand, and I don't know why it just did that to me, so let me see if I can fix that. Okay, so one thing that's important to understand is that if you have a hydrogen ion, an H+, and a hydroxide ion, they basically come together to form water. So we can rewrite 2H plus and 2OH minus as 2 water molecules. So I'm going to go ahead and do that. So this 2H plus and 2H minuses, that becomes 2 water molecules, right? And notice also that we have 1 water molecule on the left and we have 2 water molecules on the right. One of the water molecules on the left is going to cancel out with one of the water molecules on the right, and so we can rewrite it further as 1 water molecule on the right and no water molecules on the left, right? So this equation just simplified down quite a bit for us, even though it's still pretty complicated, right? So this is our half reaction so far, right? We have 2 OHs plus sulfite ion yields sulfate ion plus 1 water molecule, okay? Okay, so we're going to take that same approach to our reduction half reaction. Got a message from Aaron Pineda. It says, hello, huge fan. Hello, right back at you. Thank you very much for consuming my content, and thank you for joining the stream. I love you guys. CM Abraham says, will these live streams be posted? Going to start studying electrochemistry soon. Yes, they will be posted. Basically, if I can post it tomorrow, I have to wait for the video to process so that I can trim it down. And then once it's trimmed down, then I can add all the chapters and timestamps and all that kind of stuff. And then once I do that, I can add like an end screen, make sure everything's going well with the description and thumbnail and this and that. And then I finally publish it for anybody who wants to view it Thank you for your interest. Okay, so where were we? Oh yes, we were balancing our reduction half reaction with respect to mass. Every element other than hydrogen oxygen is already balanced because we have one manganese atom on both sides of this reduction half reaction. The next step is to balance oxygen by adding water, right? So I'm going to add how many water molecules? I'm going to add 4 water molecules, 4 H2O, right? Because I have 4 oxygen atoms over here on the left-hand side of the equation. Then I need to balance hydrogen by adding H+. How many H pluses do I need to add? Well, it looks like I need to add 8 H pluses because those 4 water molecules have 8 hydrogen atoms within them, right? And then what I need to do is I need to neutralize the H pluses. And again, this step only applies to basic solution, right? I need to neutralize the H pluses by adding the same number of OH minuses, and I need to add that number of OH minuses to both sides of this half reaction. So this equation is going to get pretty long, so I'm just going to take the whole thing over here if I can and drag it. I think that's probably a good spot. Okay, so since I added 8 H pluses, I'm going to add 8 OH minuses, and I also need to add 8 OH minuses over here. That's how you take care of that step. 8 OH pluses and 8 OH minuses, that can be rewritten as 8 water molecules. So I'm going to go ahead and do that. 8 water molecules, right? And then notice that we have 8 waters on the left, 4 waters on the right. So all 4 of these waters over here can cancel out with 4 of the waters over here on the left. And so I can rewrite this as 4 water molecules. And then these 4 water molecules basically go away, right? And so our reduction half reaction breaks down to this equation where we have 4 water molecules reacting with permanganate ion to produce a manganese 2+ ion and 8 hydroxide ions. Okay, so that step is done, right? And again, very, very important to understand the difference between how this is done in basic solution versus how it's done in acidic solution, right? All right, so let's move on and go to the next step. So that's going to be step 4. CM Abraham says, thank you so much. Love your content. Thank you. Thank you for your kind words. I really, really appreciate it. And that goes for everybody in here. Thank you for watching. Thank you for commenting. Thank you for chatting. I love you guys. This is why I do this stuff. It's for you guys. It's definitely not for the money. I'll tell you that, because the money is not very good. Put it to you this way. If I delivered pizza for like 2-3 nights a week, I would make way more money than I do here. So, all right. So step 4 is to balance each half reaction with respect to charge by adding electrons, right? So how many electrons do we need to add to the product side of our oxidation half reaction, right? Well, let's figure out what the charge is, right? So it looks like we have 2 minuses, right? So that's -2. Let me do this in another color here. I'll just choose this pink or purplish color here. So we have -2 coming from the hydroxides, and we have -2 coming from our sulfites, right? And then over here for our sulfate, we have -2. So it looks like we have -4 on the left, -2 on the right. So that means I need to add 2 electrons at -1 apiece to make up that difference, to make sure that we have a total charge of -4 on both sides of our oxidation half reaction. So I added 2 electrons over there. And then over here on our reduction half reaction, we need to add some electrons to the reactant side of our reduction half reaction. How many electrons do we need to add, right? Well, it looks like we have -8 over here for our hydroxides. We have +2 for those manganese. So that means we have a total charge of -6 over here. And then it looks like we have, what do we have? We have MnO4 minus, so that's a -1. So basically it looks like I need to add 5 electrons, because 5 electrons plus the 1 minus charge coming from that permanganate ion is going to be -6, which equates to the -6 charge over here on the right hand side of the reduction half reaction, right? Okay, so this is starting to get pretty long-winded and complicated, as balancing redox equations tends to get. So that's step 4. Let's move right along to step 5. So we are closing in on being done with this. So here we go. Here's step 5. All right, so this is where it's going to start to get really, really convoluted. So step 5 says to make the number of electrons in both half reactions equal by multiplying one or both of the half reactions by a factor, right? So we need to make the number of electrons equal for both sides. So notice that our oxidation half reaction has 2 electrons, our reduction half reaction has 5 electrons, so we need to basically find the least common multiple of 2 and 5, which is 10, right? So we're going to end up with 10 electrons for both of our equations, and so that means that we need to multiply our oxidation half reaction by 5, and we need to multiply our reduction half reaction by 2, right? So if we turn our attention to our oxidation half reaction, we're going to multiply everything in this entire equation by a factor of 5. So let's go ahead and get to work. So our 2 hydroxide ions, if we multiply that by 5, that's going to be 10 OH minuses. Our sulfites, SO3 2 minuses, we're going to multiply that by 5. That's going to become 5 SO3 2 minuses. For those sulfates, those SO4 2 minuses, we're going to multiply that by 5. That's going to become 5 SO4 2 minuses. For the water, we're going to multiply that by 5. That's going to be 5 water molecules. And then multiply our 2 electrons by 5. That's going to be 10 electrons. Okay, so we just multiplied our entire oxidation half reaction by a factor of 5. Everybody still with me here? I certainly hope so, because we are moving on. So this reduction half reaction, we're going to multiply everything by 2. So our 5 electrons, we're going to multiply that by 2. That's going to give us 10 electrons. Our 4 water molecules, we're going to multiply that by 2. And that's going to give us 8 water molecules. Our permanganate ion, we're going to multiply that by 2. That's going to give us 2 of those permanganate ions. So I'll try to squeeze that in, plus 2 permanganate ions. And then our manganese 2+ ion, we're going to multiply that by 2 as well. That's going to give us 2 of these manganese ions. And then our 8 hydroxide ions, that's going to become 16 hydroxide ions, because we're going to multiply that 8 by 2. So it's going to be 16 hydroxides. So yeah, these redox equations, they really do get pretty long-winded, and it's pretty easy to mess up if you're not, like if you have like really shitty handwriting or something, and you're you just like can't read your own handwriting and you just get lost in it. So make sure you're writing clearly and you're taking your time and you're practicing. Practice makes perfect, right? Okay, so that's step 5. We now have the number of electrons equal for both of our half reactions. So we're going to move right along to step 6. So here comes step 6. Step 6 tells us to add the 2 half reactions together, canceling electrons and other species as necessary. Okay, so we can tell that when we add these 2 half reactions together, the 10 electrons are obviously going to cancel. That's kind of the whole point, right? And then what else can we cancel here, right? It looks like 5 of our waters can cancel out with 5 of our 8 waters over here, giving us 3 waters, right? And then what else can we cancel? Well, we have 10 hydroxides over here and 16 over here. So we can just completely cancel out these 10 hydroxides. Actually, you know what? Let me just strike that out like this, like I've been doing. And that's going to leave us with 6 hydroxides over here, right? 6 hydroxides over here on the right. What else? Is there anything else that we can cancel out? Doesn't look like we can. Okay, so now we're at the point where we can write the overall summation equation of having added our 2 half reactions together. And so we just need to write everything out that hasn't canceled out, basically, right? So we're going to have 5 of our sulfites, 5 SO3 2 minuses, plus 3 water molecules, plus what else? It's going to be plus our 2 MnO4 minuses, and that's going to give us, that takes care of the reactants. And then for the products, we're going to have 5 SO4 2 minuses plus 2 Mn2 pluses plus 6 hydroxide ions, 6 OH minuses. Okay, so what I'm going to do is I'm going to erase our half reactions because we no longer need them. Then what I'm going to do is I'm going to take our overall reaction here that we've worked so hard to get to this point, and I'm going to bring that to the top. And then finally, we're going to move on to step 7 of this 7-step process. So let me go ahead and copy and paste that in here. By the way, those of you who've been watching the whole time, thank you for being here. I hope this has been valuable content, and I would also hope that you would let me know if it wasn't valuable content. I can handle the harshest of criticism, believe me. So step 7 is to verify that the reaction is balanced. Pretty straightforward. We just need to set up our table of reactants and products. That's going to be our columns in this table, right? And then we're going to list every element as a row. So we have sulfur, we have oxygen, we have hydrogen, we have manganese, and of course we have the charge, right? So we need to count everything, make sure it all checks out. So it looks like we have 5 sulfur atoms on the reactant side. It looks like we also have 5 sulfur atoms on the product side. Oxygen, what do we have? There's a lot of oxygen, right? So let's count them up. We have 5 times 3, so that's 15 over here. We have 3 over here. We have 2 times 4, that's 8 over here. So 15 plus 3, that's 18, plus another 8. 18 plus 8, that's 26 oxygens. Do we also have 26 oxygens over here on the left or on the right? Let's see. We have 20 oxygens over here, 5 times 4, and we have 6 oxygens. So yeah, we got 26 oxygens. So it looks pretty good so far. It looks like this equation is going to be balanced, which is good because that means I haven't messed up somewhere. Hydrogen. What does hydrogen look like? Well, we have 6 hydrogens over here on the left-hand side, and we have 6 hydrogens over here, so that checks out. Manganese, we have 2 manganese over here on the left-hand side. We have 2 manganese over there, so that checks out. And the charge, let's look at the charge and make sure that the charge is balanced, right? So we have 5 of these 2 minuses, so that's minus 10 over there. We have 2 of these minus 1, so that's minus 2, so that makes the total charge minus 12 on the left-hand side. Do we have a total charge of minus 12 on the right? I hope we do. So 5 of these 2 minuses, that's minus 10. 2 of these 2 pluses, that's plus 4. And then we have 6, these minus, that's minus 6. So that's minus 16 plus 4, so that's minus 12. So yes, this equation is indeed balanced both atomically and electrically. And that, my friends, is how you balance the equation for a redox reaction taking place in basic solution. All right, everyone. So that is going to do it. Sorry about the music. I keep forgetting to turn that off at the intro. That is going to do it for this Electrochemistry Volume 1 live stream. Again, I do apologize if this one was a little dry and a little boring. I did get a lot of engagement, and for that I am very, very, very thankful. Thank you guys so much for dropping your thoughts in the chat and for all the kind words. Really, really appreciate it. And then so yeah, next week we're going to talk about the interesting stuff. We're going to talk about galvanic cells. We're going to talk about standard like reduction potentials and electromotive force and all that kind of stuff. Thomas Shelby says, have a doubt. Oh, I'm sorry that you have a doubt. Unfortunately, I can't stay long because I can hear my daughter crying. I need to go help calm her down. So love you guys. Thanks for watching. And I hope to see you next week, same time, where we will discuss electrochemistry in further detail, digging deeper and deeper into the content. All right. Love you guys. Take care.